I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solutions of 3 problems from the section Linear Algebra and that have appeared in the CSIR National Eligibility Test on December 15th, 2019. These questions are suitable for all these examinations. Right. This is the question with this question ID from part B for 3 marks. And the question is related to system of linear equations. The given question is, let A is equal to the 3 by 3 matrix 2 0 5 1 2 3 minus 5 1 minus 1 5 1. The system of linear equations Ax is equal to y has a solution. We are given 4 options. Option 1, only for y is equal to the column vector x 0 0 x belongs to R. Option 2, only for y is equal to the column vector 0 y 0 y belongs to R. Option 3, only for y is equal to 0 y z, the column vector 0 y z belongs to R. Option 4, for all y belongs to R cube. For all column vectors of y belongs to R cube. Right. Let's now discuss the solution of the problem in detail. So we have that matrix, 3 by 3 matrix, and we are given the system of linear equations Ax is equal to y, and we are asked to find under what conditions it has a solution. So we have that system Ax is equal to y, and this system has a solution if and only if the rank of the augmented matrix A with the column vector y is equal to the rank of the coefficient matrix capital A. Right. And y is completely unknown here. So we will consider only A and find out its row reduced echelon form, and thereby we find its rank. So that is the matrix. So what I do is I perform elementary row operations on it and obtain its row reduced echelon form. We interchange the first 2 rows. After the interchange, this is the matrix. Right. Now we want to make it this position 0 and this position 0. To do so, we apply this elementary transformation. R2 is R2 minus 2R1, thereby this becomes 0. R3 is given by R3 plus R1, thereby this becomes 0. Perform the operations, then we get this matrix. Agreed. And we are interested in finding the rank of this one. Therefore, we perform such a elementary transformation in order to make this one 0. Right. R3 is 4R3 plus 7R2, and thereby this becomes 0. And the resulting matrix is the matrix, this one. It is in the row reduced echelon form. Right. And what is the rank of this A? The rank of A is the number of non-zero rows in the row reduced echelon form. The number of non-zero rows are 3. Therefore, the rank of A is 3. When the rank of A is 3, the rank of the augmented matrix A with y is also 3. Therefore, they are equal. Then the rank of the augmented matrix is equal to the rank of the coefficient matrix is equal to 3. That is equal to what is 3? 3 is the number of variables number of variables. So recall now, the system Ax is equal to y has a unique solution. What is that unique solution? X is equal to A inverse y. A inverse exists because the rank of A is 3. So that unique solution is X is A inverse y, and this is true for all y belongs to R cube. So solution, it has a solution for all y belongs to R cube. Let's look at our options. Our answer for all y belongs to R cube appears against option 4. Therefore, the answer to this question is option 4. That is the detailed discussion of the solution of this problem. It is a very simple and straightforward problem. Let's move to the next question. This is the question with question ID, this one, from part B for 3 marks. And the question is on the concept of matrix representation of a linear transformation. Let V be a vector space of dimension 3 over the field of real numbers. Let T, V to V, be a linear transformation, that is, T is a linear operator given by the matrix A is given by 3 by 3 matrix 1 minus 1 0, 1 minus 4 3, minus 2 5, minus 3 with respect to the ordered basis V1, V2, V3. This is the basis of V. Then what is this A? A is the matrix of T with respect to the basis B, where the basis B is V1, V2, V3. Then which of the following statements is true? We are given 4 options. Option 1, T of V3 is 0. Option 2, T of V1 plus V2 is 0. Option 3, T of V1 plus V2 plus V3 is 0. Option 4, T of V1 plus V3 is equal to T of V2. Let's now discuss the solution of the problem in detail. We have V, a vector space of dimension 3 over R. And we have T is a linear operator on V. And given by the matrix A, this one 1 minus 1 0, 1 minus 4 3, minus 2 5, minus 3 with respect to an ordered basis capital B is equal to the set consisting of V1, V2, V3 of V. That means this matrix A is the matrix of the linear operator T with respect to this basis B. Right. Now T of V will be AV, where V belongs to R cube. What is R? What is V? V is a column vector. And this column vector is to be expressed in terms of y1, y2, y3, xy1 plus yv2, xv1 plus yv2 plus zv3. Then xyz will be the coordinate vector. Therefore, V is represented by the coordinate vector, the column vector xyz. Agreed? Agreed? So, we are all familiar with all these concepts. Let's get into the next slide. Right. We take T of V3 is equal to 0. How V3 is written? V3 is equal to 0 V1 plus 0 V2 plus 1 V3 written in terms of the basis B. And the column vector is 0, 0, 1. Now, T of V3 is A times V3, A multiplied by V3. That is the matrix A multiplied by V3 is the column vector 0, 0, 1. Multiply, you will get 0, 3 minus 3, which is not equal to 0. So, that's the option 1 is not satisfied. Right. Option 2, T of V1 plus V2 is 0. So, V1 plus V2 is 1 V1 plus 1 V2, 0 plus 0 V3, that is 1, 1, 0. So, T of V1 plus V2 is A multiplied by V1 plus V2, that is the matrix multiplied by 1, 1, 0. And multiply, you will get 0, minus 3, 3. Agreed. This is also not satisfied. Let's look at V1 plus V2 plus V3. its column vector will be 1, 1, 1. So option 3, T of V1 plus V2 plus V3 is 0. That is the matrix multiplied by 1, 1, 1, right? A multiplied by V1, 1, 1, 1, right? So that is, if you multiply, you will get 0, 0, 0, that is the vector 0. Thus, the option 3 is true. It is satisfied. What about option 4? T of V1 plus V3 is equal to T of V2. It is not true. It is very clear. Why? We have T of V1 plus V2 plus V3 is equal to 0. We have seen in option 3. And T is a linear transformation. Therefore, T of V1 plus V3 plus T of V2 is equal to 0. It is linear. This implies T of V1 plus V2 is equal to minus T of V2, and it is not plus T of V2. Therefore, option 4 is not satisfied. Is not true. Option 1 is also not true. Option 2 is also not true. Option 4 is not true. And option 3 is true. Therefore, the answer to this question is option 3. That is the detailed discussion of the solution of this problem, and it is a very simple and straightforward question again. Right, we move to the last question in this video, and this is the question with the question ID this one from part B for 3 marks. And this question is related to the concepts of inner product and bilinear form. The given question is C closed interval 0 to 1 with the space of continuous real valued functions on the closed interval 0, 1. Define bracket f comma g is equal to integral 0 to 1 f of t g of t square dt for all f comma g belongs to C close bracket 0 to 1. Then which of the following statements is true? The question is this definition of bracket is qualifying to be an inner product, or is it qualifying to be a bilinear form? Right. We are given 4 options. Option 1, bracket is an inner product on C01. Bracket 2 is a bilinear form on C01 but not an inner product on C01. Option 3 is not a bilinear form on C01. Option 4, bracket f comma f greater than or equal to 0 for all f belong to C01. Means to say, is the condition of positivity in the definition of the inner product satisfied? That's the question of, that's the option 4. Right. Let's now discuss the solution of the problem in detail. We first take option 4. That is bracket f comma f greater than or equal to 0 for all f belong to C01. And we also consider option 1, bracket is an inner product on C01. So first go here. Now let f of x is equal to minus x. Clearly, f is a continuous real valued function defined on the closed and bounded interval 0 to 1. Therefore, f belongs to C01. Now, bracket f comma f is integral 0 to 1 ft minus t into g of t square, that is minus t square dt. That is equal to minus integral 0 to 1 t cube dt. That is equal to minus, after integration, t power 4 by 4 to be evaluated between the limits t is equal to 0 to 1. On evaluation, you will get minus 1 by 4, which is negative. Now, option 4 is not true. Straight away, option 4 is not true. But what is this condition? What is this condition? This condition is the positivity, the condition of positivity in the inner product definition. That is v comma v bracket is greater than or equal to 0 for all v belongs to v. And it should satisfy, the bracket should satisfy symmetry, linearity in first slot. and positivity, positive definiteness. The positivity is not satisfied in this, therefore it is not an inner product. The condition of positivity for all, that is bracket f comma f greater than or equal to 0 for all f belongs to C01 is not satisfied, therefore this is not an inner product on C01. Thus option 1 is not true. Move to the next slide. We have the definition of the bracket, right? And we take option 2. It is a bilinear form on C01 but not an inner product. We have already seen it's not an inner product. Option 3 is not a bilinear form on C01. Now Fg, that is the bracket Fg, defines a bilinear form if it is linear in first and second slots. Linear in F, linear in G. Now we take the homogeneity in the second slot. That is bracket f comma alpha g, where alpha is a real number. By definition, it is integral 0 to 1 f of t into, in brackets, alpha g of t whole square dt. Alpha is a real number. And that is alpha into g of t whole square is alpha square gt. Alpha square being a constant, it will come out. And that is equal to alpha square into integral 0 to 1 f of t gt square dt. That is alpha square into the bracket f comma g. Now, they are not equal. F of bracket f comma alpha g is not equal to alpha square bracket f comma g when alpha is not equal to 0, when alpha not equal to 1. That is, the homogeneity in the second slot is not satisfied. Therefore, it is not a bilinear form. So, the bracket is not linear in the second slot. Therefore, the bracket will not define a bilinear form. It is not a bilinear form on C01. So, option 3 is true. It is not a bilinear transformation. It is given. Yes, it is not a bilinear. Option 3 is true. And option 2 is not true. The answer to this question is option 3. That is the detailed discussion of the solution of this problem. This is also again depends only on the definitions of inner product and bilinear forms. It's also a simple and straightforward question. In this video, we have discussed 3 problems. All of them are very easy. I am sure that you have understood the solution of this problem. I thank you for watching my videos. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We hope to meet you once again in another episode of learning. Enjoy learning mathematics. Thank you.